Very good morning, students. We are meeting after a gap of 3 to 4 days. So let me quickly revise what we had done in the previous week. Okay, so first of all, am I audible? Kindly let me know. Thank you so much. So let's quickly revise DES. We had completed data encryption standard in the previous lecture. Today I'm planning to complete these three topics. That's why we are going to have two lectures. Depending upon whenever I complete the topics, I can end the session. But my main focus is on completing these three topics, that is double DES, the drawbacks or weaknesses of double DES, and then followed by triple DES, why triple DES came into picture, what is the need of triple DES, and so on. After we are done with this, we are going to start with the next cipher, or we can say the next encryption model, which is used nowadays commercially also, that is advanced encryption standard. Okay, so let's start with the revision of DES, and then I will start with double and triple DES. I will quickly revise, or I will quickly summarize all the steps over here. What happens in DES is it is basically a block cipher based on the feastal structure or the feastal cipher. I hope now you know what exactly is feastal cipher. We have already taken two lectures on that, right? So the very first thing is whatever is the plain text, it is obviously of size 64 bits. You have to divide the entire plain text, whatever you're having, into blocks of 64 bits each, right? And the diagram you can see over here, this is nothing but the representation of a single block. The same thing happens for all the blocks. We keep on appending the result of each and every block, and we get the result, that is the final ciphertext. So this is the overall schematic diagram of DES. I hope this is clear. We divide that into left plain text, right plain text, right? This is a feature structure. All the operations are performed on this right part. It goes as one of the inputs to the function. The next input is the key. The output of the function is finally XORed with the left plain text. Whatever result we get, we swap them. And for the next round, the the right plain text of the previous round becomes the left plain text of the current round. Am I clear? And similarly, the right plain text of this current round is nothing but the output of this operation, right? I hope this is clear. This is what the feasible structure is all about. And then we saw that the internal rounds of DES consist of these operations. The very first one, let me explain all of this. As you know, the plain text is nothing but the input is nothing but the 32-bit plain text, which goes inside the function block. You can say this is the function block. So basically, these four operations happen inside the function block. The very first step is key transformation. We saw what exactly is the key transformation. We know that initially we have a 56-bit key, and from those 56-bit keys, we get a 48-bit key by simple transformations. As you can see, let me show you the table. This was the table we saw. Sorry, it's above. Yeah, this was the table we saw. The key transformation like this. Depending upon the round number, we do some sort of shifts. For example, if round number is 1, 2, 9, or 16, we shift the positions by 1. For all other rounds, there will be a shift of 2, cyclic left shift, right? And then after the shift, we refer this table, do the transposition, and whatever is the current 48-bit value, we use it as the round key, which is of size 48 bits. So let me reiterate once again. The effective key, or we can say the key of DES, is nothing but 56 bits, but the round key is nothing but of size 48 bits. Am I clear? Kindly let me know in the chat box. Any confusions with this so far? Okay. What about others? Is it fine? Is this clear? Because for double DES and triple DES, it's very simple to understand if you know what exactly DES is all about. Fine. So I hope this is clear. A division not getting response from your side. And one more thing, if my video becomes a little laggy, do let me know in between so that I can switch to my other network. If it's fine, I can continue. Okay, so this is all about the internal structure of key transformation. The next step is expansion permutation. So as you know, the right plain text is of size 32 bits, but Now the key is of size 48 bits. Obviously, we can't do operations between a 32-bit value and a 48-bit value. So what we did, we expanded the 32-bit values to a 48-bit value by simply adding 16 bits. That is, we are expanding the 32-bit plain text to form a 48-bit values by adding 16 bits. And we also saw that those 16 bits cannot be added randomly. They have certain transformations. We saw how to do that. Let me show you that. I hope this diagram is clear. This is what we did, if you remember. From 4 bits input, we got 6-bit output. It was very simple. Copy the first, second, third, and fourth bit into second, third, fourth, and fifth positions of the 6-bit register. The first bit is nothing but the last bit of the previous block, that is input block, and the last bit of this output block is nothing but the first bit of the next input block. And this keeps on happening in the daisy chaining fashion, and ultimately we repeat 16-bit positions. And this is how we got the 48-bit value. Now we have the 48-bit value, that is the right plain text. We simply need to do some operations on those and we will get the output. After this, we also came to know that at the end we need to XOR with the 32-bit value only, yes or no. But now we are having a 48-bit value, so we need to replace this 48-bit into a 32-bit back. So we saw that with the help of some S boxes or substitution boxes, we can do that. Once we get the output, we change the positions of the uh, final temporary ciphertext, we can call it, by using some p-box permutation. And whatever result we got, we XORed that with the LPT, and that became your new RPT, and so on. So this was the internal structure of the Feastel structure, or we can say the data encryption standard. Now am I clear? This is what we studied in the last lecture, and this is all about data encryption standard. So if you're not having any doubts, I can start straight away with the next topic, that is double DES. Okay, kindly give me your responses. A division, I'm not getting a single response from your side. Okay, fine with B. Okay, thanks a lot. So let's move ahead with our first topic of the day, that is double DES. I hope I had given one homework, the weaknesses or drawbacks of double DES. If you have done some research, we had 3 days time, right? So you must have done that. Kindly let me know if you have the answers for that particular question I gave you. Drawbacks or weaknesses of double DES. Any answers from your side? Yes, if you are having answers, kindly let me know. This was the internal structure of double DES, as you can see over here. Double DES is nothing but applying DES twice with different set of keys. So if you see this expression over here, the ciphertext CT is nothing but, it is an output which we get after applying this expression. That is, we first of all encrypt the plain text using the first key. Whatever is the result, the temporary result, we encrypt that using one more key, that is K2. And whatever is the result after applying the keys twice, we get the ciphertext. Am I clear? So just have a look at this diagram. It's very simple. There's a plain text. We encrypt that using K1. Obviously, the key size is 56 bits. The temporary ciphertext which we get, we encrypt it again with another key of size 56 bit, that is K2. And after that, we receive the ciphertext. Very, very much simple, very much clear. I'm not focusing into the internal structure of these boxes, because these are nothing but the entire operation of DES inside this box. So just don't think that it is only a single box. It is nothing but the entire operations that we had seen in the last lecture, and today also during the initial revision session. It is nothing but a complete operation of DES that happens inside those boxes. Fine. So in total, we are having 112 bits, right? As compared to DES, which used to have only 56 bits, it is having 112 bits. So that adds a little bit of security to the existing DES. Am I clear? Next step is the decryption part. The decryption part is exactly similar. Just make sure. I guess I had by mistake inverted the positions of the keys in the previous lecture, so make that correction over there. What happens is you encrypt initially with K1, and whatever result you get, you encrypt it with K2. So at the receiver's side, the first decryption should begin with key K2 and then key 1, K1. Yes or no? Kindly let me know. Because it is exactly in the reverse order, if I'm not wrong. It makes sense, right? So first we encrypt with K1. Whatever is the result of the temporary ciphertext, we encrypt it with K2. So it should happen exactly in the reverse order. And that is nothing but we should decrypt initially with K2 and then with K1. So this is the diagram. So decrypt the ciphertext with K2. Whatever resultant temporary plain text you will get, again decrypt that with K1 and you will get the final plain text. Is it clear? This is what double encryption standard, sorry, double data encryption standard is all about. That is double DES. It's very simple. So I have to write what exactly is DES in short, and then explain this diagram, explain this expression that I had shown you just now. That will be your answer for a 5-mark question. But at the end, you should also write what are the drawbacks or possible attacks on double DES. Otherwise, what is the need of triple DES? Am I correct? So there has to be some sort of drawback which leads to the invention or which leads to the experimentation of triple DES. Am I clear? So that is what I am looking as an answer from your side. What exactly could be the drawback? Just have a look at this diagram and try to tell me what could be the drawback of double DES. At least give it a try. Okay, man in the middle. Okay, Praful has given an answer, man in the middle. What about others? Correct, Rishikesh. The answer is meet in the middle. Man in the middle is not the accurate answer I'm looking for. The answer is meet in the middle. Meet at the center. This is what I'm looking for. I will explain that entire attack in detail. So meet in the middle is the exact attack I'm looking for. I'm writing it over here. You must have heard about man in the middle. If not, let me explain. Man in the middle is nothing but it's like a communication is happening between the sender and the receiver. You intercept the communication and take hostage, or what you can say, take complete access of the entire communication. You can read whatever is being transmitted by the sender to the receiver. You can make changes. You can basically hijack the session. So session hijacking is nothing but an application of man in the middle attack. But over here, what we are trying to focus is that that is what we call as meet in the middle. Now, meet in the middle is somewhat a variation of man in the middle. Just have a look what I'm talking about. Any idea what exactly could this be? First of all, try to give answers and try to make it as interactive as possible. You can even unmute yourself if you wish and let me know the answers. What could be meet in the middle attack? Meet as in meet someone. It's similar to that. You start from one end and meet at the center. This is what is the application, or what we can say the significance of meet in the middle. So let me explain it once again. Okay. So I'm just giving you a scenario. This is your first plain text, which is getting encrypted, right? This is your plain text, and I'm encrypting that with K1. You will get a temporary result. Fine. In double DS, what happens? You encrypt this value again with your second key. Yes or no? And you will get the ciphertext. Simple. The same diagram only. I am redrawn it once again. Any confusion with this? Kindly let me know in the chat box. Yes, come on. Kindly be interactive as much as possible. Fine. Okay. Now you only tell me what could be the attack possible. What could be the possible attack on this? Basically, we need to find out K1 and K2. Yes or no? If we come to know what is K1 and what is K2, then we can access the entire communication network. Yes or no? So the main thing which is vulnerable over here is a temporary value. Very good. Access of temporary data. Correct. Very good answers from your side. Now, how to do so? I'm giving you a very what you can say. I'm giving you an example or illustration. Suppose I keep on trying. Suppose I encrypt this particular plain text with K1. Okay, I have this message. What I will do is I will encrypt this message with K1. Just a minute. I will just come back. Yeah. So I was just saying that you have to encrypt the plain text with K1. Okay. Now what the attacker tries to do is attacker will try n number of combinations of K1. Okay. I myself being an attacker, what I will do is if I come to know that there are 26 characters, obviously there are uh, 26 alphabets. Just take an example that this is a binary value. So only possible combinations would be 2 raised to 56. Yes or no? Because this is DS we are talking about. In the case of double DS, it simply becomes 2 raised to 112. Yes or no? Including both the sides. Am I correct or not? Fine. The 0 and 1 being the binary values. So let me show you the explanation first, then the things will be very clear. What I was talking about. The meat in the middle is basically this sort of a thing. What happens is, first encrypt all the 2 raised to 56 possible values of K1 and store these results in a table. And then sort the table by the values of X. So what I mean to say is, I myself being the attacker, what I will do is, I will first of all encrypt with the use of K1 as the key. So what I will do is I will encrypt a message with K1, I will encrypt a message with K2, I will encrypt a message with K3 and so on. Is this clear or not? I'm talking about the crypt analysis part. If you want me to explain it once again, let me just read it once again. We encrypt P for all 2 raised to 56 possible values of K1, store these results in a table, and then sort the table by the values of X. Do you need any more further explanation? I will repeat it once again. Just have a look. I am the attacker. Okay. Just assume that I am performing crypt analysis. Now, crypt analysis, as you all know, it is the process of breaking the cipher. Yes or no? The very first lecture we did this. Kindly let me know. I will again explain the process from the beginning. Don't worry. So I am just assuming that I know what is the plain text because I myself has created this cipher, right? So I'm just assuming that I know what is the plain text. Fine. So what I will do is I will try all the possible combinations of K1 on that plain text. How many possible combinations are there? There are 2 raised to 56 possible combinations. Yes or no? Because the key is of size 56 bits and I know that the input is only in terms of zeros and ones. So it would be 2 raised to 56 possible combinations of the encrypted text. Yes or no? Is it clear? Kindly let me know. Fine. Now, what I will do is I will start decrypting this particular ciphertext. Obviously, if I am the owner of this encryption model, I will have access to the plain text. I will have access to the ciphertext. What I will do is I will encrypt a message. For example, hello. I will encrypt this hello with a key K1 and I will get the result, suppose PQRST. So this is my plain text. This is my ciphertext. Yes or no? I'm K1 and K2, right? I'm doing double encryption. Fine. So what I have access to, I right now have the access to the plain text. I also have access to the ciphertext. I'm trying to check whether my encryption model is secure enough or not. Fine. So what I will do, I will first of all encrypt this hello with 2 raised to 56 possible combinations of keys. That is K1. Similarly, I will try to decrypt this PQRST with 2 raised to 56 possible combinations of K2. Am I making sense now? I'm encrypting hello and decrypting PQRST simultaneously from both the sides. Is it making sense? Kindly let me know. Are you understanding what I'm trying to explain? Yes, B division, A division, yes or no? Do you need any further explanation? See, the basic funda is I have created an algorithm and I want to check whether my algorithm is strong enough or not. So what I will do, I will encrypt the plain text with 2 raised to 56 possible combinations of keys and store them in a table. Similarly, I will start decrypting the ciphertext with 2 raised to 56 possible combinations of key K2 and again store them in a table. Correct. We are trying that. Yeah, correct. We are trying to get the temporary value from both the ends. That is what I'm trying to say. So what happens now? I will now eventually have a table with key K1 over here and some temporary value over here. Similarly, I will have one more table with key K2 and temporary value over here. So at one point of time, I will have the temporary values present in both the tables. Yes or no? Obviously, it has to be same because 0 and 1, these are the only possible combinations of 2 raised to 56 times, right? So at one point of time in the table, there has to be an entry which will be same over here in this table as well as in this table. So the corresponding values of K1 and K2 are nothing but the keys using which you have encrypted the plain text hello. Am I clear now? Yes or no? So we are trying to find the temporary value once encrypting from the left side and decrypting from the right side. So we are doing this from both the ends simultaneously until we get the temporary value. Am I clear? Fine now. So if the attacker has got access to the temporary value, it is quite possible that the attacker comes in between and gains access to the temporary value. Then what he will do is he will encrypt using 2 raised to 56 possible combinations of the key, and at the same time he will try to decrypt. At one point of time, the table will have the temporary value present in one of the rows. Fine. So the corresponding value of K1 and corresponding value of K2 are nothing but the actual keys using which you had encrypted hello and got PQRST. Am I clear? Do let me know. This is what we call as the meet in the middle attack, where both of the attackers, or we can say we start with the plain text from one end, we start with the ciphertext on one end, and meet at the center or meet in the middle. Fine. This is practically possible and one of the most useful attacks on double DES. And hence we felt the need to introduce one more cipher, that is what we know as triple DES. Am I clear now? Do you want any further explanation on this, or is it clear? Shall I move ahead? Do let me know. Okay, fine. Clear. Okay, great to know that. So let's move ahead with triple DES because obviously there were these drawbacks in double DES. That's why we felt the need to introduce triple DES. If you want, I will just keep the screen on for a few minutes or few seconds. Just read it once again. The same thing I have explained. The simplest form of multiple encryption has two encryption stages and two keys. Given a plain text P and two encryption keys K1 and K2, the ciphertext C is generated as so and so. The same thing. So what we are doing is we are applying uh, DES twice with two set of keys K1 and K2, and this is what is we know as the man in the middle attack. Just have a look. Just read it once. The algorithm known as meet in the middle attack was first described in so and so in this explanation. Okay, so it is based on the observation that if we have C is equal to this is your formula, then X is nothing but that temporary value. Okay, and D is nothing but the decryption. So C is the ciphertext, and this is the formula for decryption. So what we know, given a known pair of plaintext and ciphertext, we can start with the attack and find out the keys. So that is what we did just now. Fine. Okay. So any one of you is having idea what could be triple DS? Similar thing. Just have a look at this expression and try to explain what exactly is the difference between double and triple DS. Just have a look at this expression and tell me what is the difference. Okay, having three keys. The very first is having three keys. Fine. Dhruv, we will see what exactly is the temporary value over here. We'll see in detail. It's the same thing, but as you can see, triple DS is nothing but we encrypt the plain text once with K1, then whatever is the temporary value, we encrypt it again with K2, and whatever is the temporary value, we encrypt it again with K3. So over here, we may have multiple temporary values. We won't have a single temporary value over here as compared to double DES, right? So even if I start like this, even if I start from the left side and right side at the same time, we won't get access to the temporary values. Let me show you how. This is our first phase, our first encrypt block. If I start from here with K1, I will have one temporary value, temp1. Okay, I will encrypt this again with K2. I will once again get another temporary value. And I will finally encrypt this again with K3. And this will be my ciphertext. Now, if I try to perform meet in the middle attack, I will get this and this. But what about the key K2? Obviously, I will get hold of K1 and K3, but can I access K2? Yes or no? Now you only tell me. Is it clear or not? If I try to perform meet in the middle attack from both the sides simultaneously, I will obviously at one point of time get access to K1 and temp1, and at one point of time I will get access to temp2 also if I start from here. But what about key K2? I will get access to K1 and K3, but there is still one more unknown, which is what we know as K2. Is it clear from this diagram? Yes or no? Is it secure? Is it more secure as compared to double DS? Obviously, because we still have one unknown, and that unknown is really, we can say, a very huge factor in decrypting or breaking a cipher, because we will still need to apply brute force. Obviously, it is not that difficult to crack 2 raised to 56 bit values, because nowadays we have high performance computers and hardware, so it is not that a big deal to do that. But at the time of invention of this cipher, it was a huge deal, or we can say it was a big deal, right? So that time this cipher came, that this cipher became very popular. Nowadays it has been cracked with the obvious reasons. Fine, because we simply need to perform brute forcing and try to find out at which point of time this temp1 and temp2 will give me the answer. So that is possible. So we can say that even if we try to add n number of encryption steps in between, considering today's modern age computers, it won't be that difficult to crack it, because ultimately the internal functioning will remain same. Yes or no? So at that point of time, double DS was having few major drawbacks, which was overcome using triple DS. But now triple DS also can be cracked easily. So we are not focusing on data encryption standard as a commercial application or as a commercial encryption algorithm. So to overcome these difficulties, we came out with advanced encryption standard. So I will focus upon that later on. But first of all, let me tell you that there are two variants of triple DES. What could be the variants? Any idea? It is very simple with the help of three keys, K1, K2, K3. But can we do triple DES with two keys? That is what is my next question is all about. Triple DES with two keys. Is it possible? The architecture may look a little childish to you, but it is possible. How? Any ideas? Can we perform triple DES with two keys? In fact, triple DES with two keys and triple DES with three keys will give the equal amount of security, but the hardware requirement will be lesser if we consider only two keys. Any one of the keys we have to repeat two times, Dhruv. So it depends basically which key you are going to repeat it. But obviously we need to repeat some key. ज्योति K3 नहीं होगा ना, it will be K2. We are making use of two keys ना. Keep on trying. What could be the sequence? Encrypt, 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 or anything in between. I'm giving you beautiful hints. What exactly is encryption or decryption? It is basically a mathematical operation only, right? Yes or no? And most of these consist of XORs. Am I making sense? Encryption and decryptions are basically a block, a function block. You saw in DES also, it basically consisted of XOR operations. So can we invert XOR operations? Yes or no? We know that A XOR B XOR C is nothing but A XOR C XOR B. Aren't they the same thing? We can add a bracket also in between. They will give you the same result. Yes or no? Clear, right? So what we can say is double DS with two keys is very simple. The thing is, it is like this. Just have a look. We encrypt the plain text with K1. Whatever is the result, we apply the decryption algorithm using K2. I will come back to it, don't worry. And whatever is the temporary result, we again apply encryption with K1. So this is what I was saying just now, that encryption and decryption algorithms are basically interchangeable, right? So what this algorithm is all about, it is first of all encrypting the plain text with K1. Whatever result you are getting, the temporary result, I'm writing temp over here, you are decrypting that. In simple sense, you can't decrypt that like this. It is nothing but you are applying the decryption function or decryption algorithm over here just to confuse the attacker. Am I making sense? Right? And whatever result you are getting, you are again applying finally the encryption algorithm with K1, and you will get the result as ciphertext. Am I clear? Am I making sense now? So that was the so basically focusing upon this XOR operation was the main thing I was looking forward, because that is what exactly happens inside the encryption and decryption blocks. Am I clear? Fine. This is what we do if we want to apply triple encryption or triple DES with two keys. If we have some hardware constraints, then we can go definitely for this sort of a thing, where we encrypt, where we apply the encryption algorithm to plain text. Whatever result we get, we apply the decryption algorithm using K2, and on that result, we again apply encryption with K1. And whatever is the result, that is a final ciphertext. Fine with this? Okay. The decryption is exactly opposite. We will get the ciphertext. You apply decryption with K1, then encryption with K2, and finally decryption with K1, and you will get the result. Fine. So if you are done with this, can we move ahead? Or if you have any doubts, you can still ask me. Because the next topic is lengthy, it will take some time. I will give you break in between as per your schedule. Don't worry. At 12:50, we can give the first break, and I will require 40 minutes or more, 40 minutes or so. So I will wind up this topic because I don't want to break in between. I don't want to break off even a single day, because you won't understand later on. You need to practice a lot. That is AES. Okay, fine. So can we move ahead? Kindly let me know. Yeah, 1 second, Jyot. These are the two equations. Just have a look. Okay, just note down the equation in 2 minutes, and I will be starting with AES in the next 2 minutes. Fine. So let's start with the next topic, that is advanced encryption standards. So you must have heard about this WhatsApp end-to-end encryption. Yes or no? Because you being computer engineers, we being computer engineers must have thorough knowledge about what exactly we are using. There was a lot of debate on the new WhatsApp policy, Facebook policy, privacy policies. So these things were in limelight, we can say. These things were in contention. What about the security of users? So you must have a thorough understanding of these sort of current affairs when it comes to security, right? So any idea what exactly is end-to-end encryption? And now you might be having this doubt that even after end-to-end encryption, the WhatsApp chats were leaked. Yes or no? Sometimes the chats are visible on social media that so and so person has leaked this chat. That is basically if they take the screenshots and share it. Otherwise, if you have end-to-end encryption protection, whatever encryption algorithm you use, you can't leak the messages like that because you need the decryption key. Otherwise, you can't leak those messages. Yes or no? That is what we call as end-to-end encryption, right? You encrypt at one end, it can be decrypted only at the other end. No one else can come in between. They can only come in between if they have the keys. Otherwise, they can't. Am I clear? So that is what this advanced encryption standard is all about. It is being used commercially since its inception because it simply replaced data encryption standards. Before AES, DES was the only method of choice, but as we have seen the various drawbacks of DES, it had to be replaced, and AES was the most suitable replacement at that time, and still now also AES, even one of the versions have been cracked, but still AES 256 is being used commercially, and AES 512 is also in production. It has been designed but not commercially uh, deployed anywhere. It is still in the process, right? So let's start. If you're having any doubts with this, you can simply ask me before I start with this encryption algorithm, and then I can simply start with it. Fine, because I'm going to need approximately 40 to 50 minutes to cover this topic, maximum 1 hour. Okay. So if you're having any doubts in between, you can ask me. Fine. So can I start with this? Do let me know in the chat box. Fine. Do refer this notes, okay? Because I have designed this from various reference books, from various sources available on the internet. So it will be really easy if you refer this. Fine. And also, if you need to brush up few topics, you can obviously check the previous videos, recording videos. Fine. So let me tell you what exactly this cipher is all about. Just have a look at this diagram. We'll start with the diagram and then I will move forward. This looks huge. It is in fact a little complex to understand, but don't worry, we'll get each and everything in detail clarified. Okay, so just have a look at this. The plain text is of size 128 bits. This is the very first difference or striking difference as compared to DES. What was the plain text size in DES? It was 64 bits, right? Yes or no? I will keep on asking questions in between. Fine. A division? Yeah, fine. So in the case of DES, the plain text size was 64 bits. In this case, the plain text is divided into blocks of size 128 bits. I can simply say that 128 bits is nothing but 16 bytes. Yes or no? One byte is how many bits? 8 bits? Yes or no? So if you multiply 16 by 8, you will get the answer as 128. Right? So it is in total 16 bytes. So what I can do is I can divide those 16 bytes into a 4 by 4 matrix. This is what we call as the input matrix or the input state, which is of size 4 into 4. Fine. I can do that where each of the cell of this matrix is nothing but 1 byte. Is it clear? This is what we call as the state array or the state matrix. Now let me make things very clear. Data encryption standard was completely based on the Feastel architecture. Yes or no? Because each and every process was thoroughly inclined with the Feastel architecture or the Feastel cipher we have seen in detail. But in this case, the advanced encryption standard does not follow the Feastel architecture. It is very much clear from the very first step itself. Yes or no? In the case of Feastel or in the case of data encryption standard, we saw that the initial plain text or input was divided into two parts, left plain text and right plain text. Does it happen here? Yes or no? No, it doesn't happen. By the way, why your attendance is short? From the last few days, I'm noticing this. Kindly make a point that you have to attend the lectures, otherwise, you won't be able to understand the topics, and I won't repeat it in the future. So, CRs, kindly make sure you inform this, percolate this information in your groups. I want complete attendance, if not complete, 80 to 90% attendance in the lectures. Fine. It's very less today, so don't make me repeat this again and again. Fine. Okay. So let's check this. The very first step is we divide whatever is the size of the plain text into 16 bytes, 16 byte blocks. Fine. And then we convert that into an array of 16 bytes itself, but it will be a 4 by 4 matrix. Fine. What happens next is you can see that it undergoes some sort of initial transformation. We'll see what exactly is that initial transformation whenever I will start with the internal rounds. Fine. After the initial transformation, we get a temporary state matrix, and from here it will go till n rounds, and the round numbers are nothing but, depending upon the size of the key, we have three variants or three set of rounds. If the size of the key is 16 bytes, that is 128 bits, we will have 10 rounds. If the number of rounds are 12, we will be having a 192-bit key or 24-byte key. Similarly, if we have 14 rounds, we will have a 32-byte key or 256-bit key. So depending upon these sizes of the keys, we have three variants of AES, that is AES 128, AES 192, and AES 256. Am I clear till here? So we are showing only the AES 128 over here as an example. So if I consider the size of the keys as 128 bits or 16 bytes, then it would range from round number 1 to round number 10. Am I clear? It will have 10 rounds. Fine. Any confusion, any doubts? Is it clear? Any doubts so far? Okay. Okay, fine. So let's move ahead. So as I was saying, over here, just have a look. Initial transformation will be subjected to a round key. I will focus upon how we get this round key from this key expansion function. What exactly is this key? I will explain it later in detail. For the time being, just think it like this. The initial input state is subjected to an initial transformation with one more input as the round key. And once the round key is being computed, once the round key is being combined with the initial transformation of the input state, we will get the initial state. From here, round number 1 will begin. Am I clear? So it was round number 0, and now we have our plain text ready. We will start with round number 1, and in each of the rounds, similar to your data encryption standard, that is a function block, we had few transformations. Over here also, inside each of the rounds, we will be having these many transformations. Just give me a minute, I'm getting a call. I will just get back. Yeah, sorry for the interruption. So yeah, I was just saying that each of these rounds will have few transformations. In the case of AES, it is having 4 transformations in each of the round till round number n minus 1. So as we are considering the AS 128 variant in this case, round number 1 till round number 9 will have all the 4 transformations. I will explain what are those transformations. But round number 10, that is the last round, will have only 3 transformations. Is it clear? Kindly let me know. We have not yet started with the actual transformations. I am simply explaining you the overall diagram of what exactly is the advanced encryption standard. Am I clear so far? Let me explain this short diagram once again. You are having a plain text of variable length, whatever could be the length. You have to divide that into blocks of 128 bits strictly. Fine, it could be n number of blocks. And then, as we know, 128 bits is nothing but 16 bytes. So we can write it as a 4 by 4 matrix. That will be nothing but 16 bytes only. That will be subjected to an initial transformation using round zero key. Now, what is round zero key? Because we need keys for each of the rounds. There are 10 rounds in total for the 128 bit variant, and round zero key is nothing but the initial key that will be used to transform our initial plain text. And once we do that, we will have our plain text ready for the further 10 rounds, right? And each of these rounds will be having four transformations inside, similar to your Feastal architecture or similar to a data encryption standard. Whereas from round number 1 to round number n minus 1, that is in this case, it is from round number 1 to round number 9, we will have four transformations in each of these rounds, except the final round, which will have only three transformations. Fine. And after the third, sorry, after each of these rounds, we will get the final ciphertext, which will be again of the same size, that is 128 bits. Am I clear now? Fine. Do let me know. Give me a thumbs up if it is clear. If it is simple enough to understand, do let me know. Okay. What about others? I want this concept to be crystal clear. This is asked 99% in each of the exam in any of the forms. In your traditional exam, it may come for 20 marks even. It may come for 10 marks. At least a 5-mark question will be asked on this, nevertheless. Fine. Okay. So let me explain the theory behind it. Just have a look. I will explain each and every line for you step by step. The first thing is the cipher takes a plain text block size of 128 bits. That is what I have shown you, or 16 bytes. Next, the key length can be 16, 24, or 32 bytes. Or in short, if you are confused with bytes, you can write that in terms of bits. That is 128 bits, 192 bits, or 256 bits. That also I have explained. Next part is depending upon the key size, it is available in three variants: AS128, AS192, or AS256. Let me tell you, AS120 or 128 has been cracked, so it is not used commercially. Even AS192 is not used that much commercially. We prefer AS256. You must have heard about SSL encryption, HTTPS. So this is where AES is used primarily, and it has many other commercial applications also. Fine. So if it is asked in the Viva, you know what to answer, right? Next is the input to the encryption and decryption algorithm is a single 128-bit block that we have discussed. Fine. Next is this block is depicted as a 4 by 4 square matrix of bytes. Again, we know what it is. Next up, this block is copied into the state array, which is modified at each stage of encryption or decryption that we have seen. Similarly, if you see, the key is also depicted as a square matrix of bytes. Over here, you can see the key is also a 4 by 4 matrix. Fine. The key is then expanded into an array of the schedule words. This is what we are going to learn next. If you see, the initial key is again of 16 bytes only, depending upon the round. In this case, we are considering it to be AES 128, so it will be having 16 bytes. If it is AES 192, it will have 24 bytes and so on. Fine. So this is how we arrange the keys. Once this key goes as an input inside this key expansion function, after following certain set of steps, certain set of rules, we will get the corresponding keys for each and every round. Am I clear? So in short, if you remember the key expansion function or the expansion permutation function of data encryption standards, there also we saw how to expand a particular 32-bit value into a 48-bit value. Yes or no? Similar kind of a concept is employed over here. Obviously, the internal functioning, internal transformations might be different, but initial concept is same only. Fine. Any doubts with this so far? Now let me show you what exactly is the key transformation function over here, or we can say key expansion function. इतना समझो, initially there is a 16-byte key which goes into this key expansion function, and the output is nothing but keys for each and every rounds. Yes or no? So in total, how many keys will be required for AES 128? You only give me answers. In total, how many keys will be required for AES 128? Come on, give me answers. I expect answers from your side. Are you sure? 10? Simran, is it 10? Nayan has given answer as 11. Okay. Rohan, are you sure it is 10? Kindly think again once. Okay, I'm getting answers from Simran, Nayan, Dhruv, Simran again. Yeah. It is 11. To see carefully, round 0 key is also extracted from the key expansion function only. So there are 10 rounds, so 10 keys will be required, and an additional round 0 key also. Am I clear? So it will be basically 11 keys that will be extracted from this key expansion function. Fine. So now tell me, have you heard about, now you know what is a byte. Do you know what is a word? Word. Yes or no? What is the size of one word? Word, double word, these are all of the storage units, you can say. I can say that one word can be expressed as 4 bytes. So what about this matrix? What will be the size of this plain text matrix, or what will be the size of this key? It will be nothing but 4 words, yes or no? The plain text or the key will be of size 4 words if I'm not wrong. Don't get confused. Just check. There are many literatures, you will see different answers in the notebooks, different answers online, but we stick to this. One word is 4 bytes. You might also encounter few answers on Google or few answers elsewhere that one word is 2 bytes. We will stick to the books that have been referred or that have been recommended by the syllabus panel. So we'll stick to that according to them. And even the researchers of AES at that time, one word was considered to be 4 bytes. So we'll stick to 4 bytes for a single word. Okay. And based on this, we will continue with our proceedings. So I can say that one word is of 4 bytes size. And similarly, the plain text is of 16 bytes. So it will be how much in size? How many words? We are now going to discuss only in terms of words, right? So what will be the size of the plain text or the key in terms of words? Kindly give me your answers. 4 words, correct. So I can say that the plain text or the key, which is nothing but a 4 by 4 matrix of 16 bytes, is nothing but 4 words. Yes? So now you only tell me what will be the size of the key expansion function. How many words will be there inside that key expansion function? I'm just assuming that it is having exactly the same size or same number of words which are required for the entire AS128. So now you only tell me how much words are required for this entire operation to take place, as there are 11 rounds. Just think of it, give me an answer, and after this we can take a break of 10 minutes. Just think of it, give me an answer before we break for 10 minutes. I'm repeating the question once again. As we require 11 keys, what is the size of each key we have discussed just now? It is 4 words, yes or no? So how many words in total would we require for the AS128 operation? Correct path has given an answer. B division, kindly give me your answers. What will be the size of the keys in words if I want to encrypt a plain text using AES 128? It is as simple as that. I have got answers from A division, no issues with it. Kindly give me your answers, B division. Just let me know that you are understanding this concept or not. Do you want me to repeat again? A division, everyone has given the correct answer, whoever has written over here. It is very simple, yes or no. 4 words for each round. How many rounds we have? 10 rounds. So it will be 40 plus the additional round, that is round 0. So it will be 44. So we will require a key, that is a total key stream of 44 words. Am I clear or not? From these 44 words, one word will be needed for each of these 11 rounds. Am I making sense now? Kindly let me know. Fine. So in total, 44 words will be needed. Now you can take a break and let's assemble at 1 p.m. Sharp. Fine. I will continue at 1 p.m. If you're having any doubts in between, you can ask me. And in the meantime, just ask your friends to join the lecture, those who have not yet joined. Fine. So let's meet at 1 p.m. Stay in the meet. We will resume at 1 p.m. I will just ask that time. Okay. And I will start at 1 p.m. Students, do let me know when we can start. Huh? Yes, can we start now? Book knowledge. Okay, A division. Okay. So let's start. As you can see, the very first transformation is nothing but the initial transformation. And for that also we require the key. The very first thing is we need the keys because just now explained, each of the rounds, 11 rounds will require a 4-word key. So how to obtain that key? Just have a look at this diagram. I will explain this in much detail. For example, this is nothing but your input plain text, which gets converted into the state matrix and so on. And similarly, you will be having your input key that is of 4 words, and it will ultimately be converted into your 11 rounds keys, that is 44-word keys, right? So let's see how to do this. What exactly is the principle behind this? It is a little trickier to understand. So stay connected. Let's see how it happens. The initial key is nothing but this 16-byte key, or what we can say 4 words, where one word is nothing but 4 bytes, right? So it is nothing but a 4-word key. So what happens? This is sent as an input to the key transformation function or key expansion function. Fine. And once that key goes inside the key expansion function, the output is nothing but a 44 word, or we can say 11 into 4 keys. Am I clear? Yes or no? You can see over here, the same thing is mentioned. You can check this diagram. It is nothing but these 4 values are nothing but W0. These 4 values are nothing but W1 and so on. So as a result, this is a 4-word key, but at the end we require 11 such 4-word keys. Yes or no? 11 4-word keys. So that is what we are going to obtain using this function, that is what we call as key expansion or key transformation. So just have a look. The AES key expansion algorithm takes as input a 4-word key and produces a linear array of 44 words. How it is done? This is nothing but like this. See this diagram first, and then I will explain how it is done. This is the diagram. It looks complicated, but trust me, it is not that complicated. You will understand each and everything in detail. What I am doing is, although you may not require to write each and every steps in the exam, but it is very important from the understanding point of view that how exactly we got hold of this, how exactly we got this key transformation, these 44 words, etc. So for that only I'm focusing on the internal arrangements, internal structures also. So just have a look what we need to do. This particular point is very important. The first 4 words are copied into the first 4 words of the expanded key. Then what happens is the remainder of the expanded key is filled with 4 words at a time. each added word wi. Now we know that we have w0 till w3. This is nothing but this only. W0 से W3 तो अपने पास है initially, but we want to have values from W4 to W44, 43. Yes or no? Obviously, we want to expand it. So for that, what we need to do is simply follow this technique. The Each added word of wi depends on the immediately preceding word wi minus 1 and the word 4 positions back, that is wi minus 4. So अभी क्या होगा, W4 क्या होगा, W5 क्या होगा, for example, what will be W5? W5 will be nothing but it will depend on the values W5 minus 1, that is it will depend on W4, and W5 minus 4, that is W1. Yes or no? If I put 5 over here in place of I, it will depend on W4 and W1. Am I clear? Yes or no? So basically there will be a function in which the value of W will depend on Wi minus 1 and Wi minus 4. Am I clear? So if we consider the value of I as 5, it will be a combination of W4 and W1. Yes or no? Kindly let me know. A division, I'm not getting any answers from you from a long time. B division is giving answers. So kindly let me know the answers. Fine. Okay. But it is not as simple as it looks. As you can see, in 3 out of the 4 cases, a simple XOR is performed. That is, if I want W5, then a simple XOR will be performed between W4 and W1. But wherever we are trying to find out something which is a multiple of 4, for example, W4, W8, W12, etc., a complex function is used, which is nothing but WG, which is nothing but G, or a generator function. We'll see later what exactly is it. If you look carefully, if I want to find out W5, I need the value of W4. Yes or no? Otherwise, I won't be able to find out the value of W5. Am I clear? It's very simple because W5 निकालने के लिए मुझे W4 का value पता होना चाहिए. And calculating W4 is not that simple. It depends on some of the factors, which is what we call as a generator. We'll see what exactly I'm talking about. Similarly, if I want to find out W9, we need the value W8 and so on. Fine. So let us see how to work out on this. This is the diagram that I'm talking about. Just have a look. All the 4 initial words are copied over here. K0, K1, K2, K3 will become W0. K4, K5, K6, K7 will become W1 and so on. It is read like this. Fine. So now we have initial values of W0, W1, W2, W3. So what we will do is see these diagrams. W4 is nothing but W0 is one of the inputs. The second input is nothing but, yeah, okay. Any issue with the B division? Are you able to see the presentation? I'm right now at this diagram. I'm explaining the diagram. Can you check my pen over here? I'm pointing at G. Is it visible in for B division? Yes or no? Okay. For A, is it visible or not? Yeah, yeah. Try once. Yeah. Try rejoining. Yeah, fine. No issues, no issues. Yeah. Okay, fine. So what I was saying is, we are basically, you can simply see this diagram. It is nothing but very simple. W4 is nothing but is calculated with the help of W0 and the output of G. Am I clear? So whatever will be the output of G, that will be XORed with W0 and you will get the answer as W4. Clear enough? Yes or no? Similarly, as you know that for finding out W5, it will be what? It will be dependent on W1 and W4. Yes or no? In between, there will be an XOR operation, right? So you can see over here, W5 is nothing but W1 XOR W4 and you will get W5. Similarly, W6 is nothing but W2 XOR W5. W7 is nothing but W3 XOR W7. So once you get the value of G, you will get the value of W4, and rest every other value can be calculated. Am I clear? It's simple. Yes or no? Yeah, don't worry, I will focus on G now. What is G? Fine. Itna samjha? Can we move ahead with what is G? Right? Okay. So now let's see what exactly is contained inside that G. As you can see, G is getting one of the inputs as W3. So here is the exact functioning of G. What we do is we simply replace, or we can say we simply change the values, or transport, or what we can say transpute the values, or basically transposition kar rahe hain hum log. So what is B1? B1 is nothing but one position to the left. So we are basically cyclically shifting all the bits one position to the left. That is, if W is 0110, it will now become 1100. We are changing the positions one bit to the left. Am I clear? Right? This is the very first step, that is rotation. Fine. Cyclic left shift by one bit. So we are rotating the positions by one bit. Next, what we are doing is we are taking those inputs and substituting them with some values. Now, don't worry, this is obviously going to be a very lengthy concept. I will explain each one of this in detail. So, whatever is the bit B1, I have to refer an S box. If you remember, we had S boxes in DES also. Similar to that, the S box in this case is like this. It will be a 16 by 16 hexadecimal value equivalent. So whatever is your B1, we will refer that in this particular table. Now B1 is nothing but an 8-bit value. Yes or no? It is an 8-bit value because it is a byte, right? So the first 4 bits of that byte will be used to check the row. That is, if my bit is like this, 1001 0011. So the first 4 bits will be used to check the row number, and the last 4 bits will be used to check the column value. Whatever value is present at the intersection, for example, this, that value will be your B1 dash. Am I clear? Yes or no? It's very simple. I think so. I suppose. I'm repeating once again. Whatever is W3, whatever is the position of W3, we do a cyclic left shift by one position or one bit, and we get B1, B2, B3, B0 again. Fine. And then what we do, check it against a table, which is the S box table, and substitute whatever value we get from that table as B1 dash, B2 dash, B3 dash, B0 dash. Any doubts with this so far? Do let me know if you face any issues. Come on, A division, B division, let me know if you're having any doubts. Clear? Jimit, what about you? What the answer? Jyoti, Rohan, Ronak, fine? Okay. Okay, so next what we need to do is we XOR these values with a 4-bit value. As you can see, not 4-bit value, 4 bytes. As you can see, the last 3 bytes over here are already filled with 0. What about this term RCJ? That is a constant. Depending upon the row number, depending upon the round number, whether if round 1, round 2, round 3, or round 4, we have to use one of these RCJ values as the first byte. And we put it over there in RCJ and XOR this 4-byte value with B1 dash, B2 dash, B3 dash, B0 dash. Whatever answer we will get, that is your G. That is the output of G, W dash. Am I clear? Let me show you this RCJ once again. This is your RCJ constant. Depending upon the round number, you will get 10 different RCJ constants. Now you might be having a doubt that sir round to 11 hai, hum to 10 hi le rahe hain. It is very clear that the first key is already present with us, right? पहले 4 words तो अपने पास है ही, so we don't need that RCJ for the first round, round 0. Yes or no? Am I clear? We already have the round 0 ka key. So that is why we don't need RCJ for that. As you can see this diagram, na, we already have W0, W1, W2, W3. So we don't need this particular value for round 0. Fine. Any doubts? Yes or no? Is it clear? So whatever will be the output of this function g, that will be XORed with W0 and we will get W4. And once we get W4, we will successively get W5, W6, W7, and so on, repeating the entire process until we get all the 44 words. Fine. Obviously, you don't need to write all this in your exam. I'm just focusing on the explanation part. So that in the Vivas, they can ask this question in the Vivas. Fine. Any doubts with this? This was the initial step, that is key transformation. Okay. Last part, Jay, which one? Okay. Okay, see, 1 second. Once we get B1 dash, B2 dash, B3 dash, and B0 dash, we have to XOR that with this 4-byte value, where the last 3 bytes are already set as 0. The only first byte will be a constant. So depending upon the round you are present right now, for example, this will be for round number 1. Next will be for round number 2. Depending upon your round number, you have to replace RCJ with these values. Got it? And once you replace this over here, you have to XOR this new 4-byte value with the existing B1 dash, B2 dash, B3 dash, B0 dash. And whatever answer you will get, that is your W dash. W dash is nothing but, in this case, it will be the output of G. Then you have to XOR that with W0 and you will get W4. Fine now? Okay. I guess it's clear now. Can we move ahead? Do give me an acknowledgement. Okay, fine. So we have completed one of the steps. As you can see over here, this is a better diagram. Each and every round will be having these 4 transformations. That is what we are going to learn now. I don't think so it will be complete by today, so no issues. Whatever topics we cover today, we'll again have a brush up in the next lecture. No issues with that. So these are the rounds that happen inside the internal blocks. As I told you that from round number 1 to round number 9, there will be 4 transformations, and in the last round, only 3 transformations will happen, except this mix column. So as you can see, these are sequential. The very first operation is substitute bytes, then shift rows, then mix column transformation, and add round key. Except in the last round, round number 10, each and every rounds have all the 4 transformations. In the last round, we don't have mixed column transformation. Now this is a standard, so they have gone for this. We can't make changes to it. It is already a known standard. Fine. So this is what we are going to do. We'll focus on the internal transformations, that is substitute bytes, shift rows, mix column transformation, and add round key. So can I move ahead? Can I proceed ahead? Kindly let me know. Students, give me an acknowledgement. Okay, fine. So just have a look. These are the detailed stages of AES. We are starting with the very first stage or very first transformation, that is substitute bytes transformation. It is one of the simplest transformations. What we need to do is I have already covered it in the previous step itself. Just have a look. There is an S box given. S box is nothing but substitution box. Now we know that each of the cells of the matrix is nothing but 1 byte. Yes or no? It is 1 byte. That is, it will be an 8-bit value. So 2 raised to 8, 256. So what we can do is, it is nothing but a 16 by 16 table over here. What we need to do is, we need to divide the first 4 parts of your byte and the last 4 bytes. The first 4 bits of your byte will be used for the rows, and the last 4 bits of your byte will be used for your column. Yes or no? So I have also taken an example just to make you understand this. Just have a look over here. Whatever input you get. Okay, now this is your plain text. Check the initial diagram. पहला diagram वापस से देखते हैं हम लोग. The very first diagram. This is your first diagram, right? You are getting this input state. So as I had told you that each and every cell over here is nothing but a byte. Yes or no? That's why it is a 4 by 4 matrix, right? Yes, come on, give me your answers. Each and every cell of the matrix is a byte, right? And we know that each byte is nothing but 8 bits. So what we are doing is we are dividing those 8 bits into two parts, left part and right part. Just understand this. So the left part is nothing but 4 bits, right part is again likewise 4 bits. What we are doing is we are considering those 4 bits as the rows and the last 4 bits as the column. So for example, there is a number 95. So what we will do, just check this number. For example, the hexadecimal number 95 references row 9, column 5. So we will divide this into two parts. The first part will be your row and second part will be your column. Yes. So this is nothing but 9 and this is nothing but 5. So what we will do, we'll check ninth row and fifth column and we will get the answer. Ninth row and fifth column. So whatever is the value present at the intersection, that is my output of that particular byte. Am I clear? Yes or no? That's why I said this is one of the simplest transformations of AES. Take the byte which you get, divide that into two parts. The left part will be the row, right part will be the column. If you want to discuss it in terms of bits, then the first 4 bits will be your row, last 4 bits will be your column. Fine? Okay. So this is the very first transformation step. I'm not going into the theory part. What you can do is you can simply read the PDF which I'm going to share. In fact, I have already shared. Oh, sorry, I have not shared yet. I will share it today after the end of this lecture. So just go through the PDF and it will be clear. Just see this diagram just for reference. This is what we are doing. X is nothing but row and Y is nothing but column. The intersection is nothing but your output. Fine. Now, how is the reverse or decryption is done? Decryption is again same, but it has an inverse S box. As you can see, what was the output? You got an output as 2A, right? So you need to check 2A over here. That is your second row and your A column. What is the value at the intersection? It is 95. Isn't it same? Yes or no? Yes, come on, A division. A division. Fine. So the inverse is exactly the same. You will have inverse S boxes as compared to a regular S box. Fine with this? Okay. So without wasting much time, I will explain that we have completed one of the rounds, one of the transformations, not rounds, that is S bytes. The next transformation is again very simple, shift rows. Just make sure that I am talking about only a single byte in this case. Fine. The entire process will repeat for all the other remaining 15 bytes as it is a 4 by 4 matrix. So this particular value 95 got replaced by 2A. In the same fashion, all the other values will be replaced. Fine, and we will get the temporary matrix present. Now we need to apply the next phase, that is shift rows. Shift rows is again very simple. What exactly we do is just take the example of this particular value over here. We do shifting as the name suggests. The first row is kept as it is. It is not changed. The second row is shifted to the left by one position. Third row is shifted to the left by two position. And the last row is shifted to the left by three positions. You can see it is very much evident in this diagram. Just have a look and let me know if you understood this. We are talking about shift row transformation. That is the second transformation of each row. Fine. What we are doing is once we are done with S box substitution, whatever is the output, we apply shift row transformation on that. Simple. So what we do, we keep the first row as it is. We make a left shift of 1 bit in the second row, left shift of 2 bits in the third row, and left shift of 3 bits in the last row. Am I clear? Any confusion with this? Do let me know. Clear. Fine. Decryption is again exactly opposite. What you need to do? If you remember playfair cipher, if we move left during encryption, then we have to move right during decryption. So here again, the same thing applies. we would need to move right while decryption. Am I clear? So what you will do, you will keep the first row as it is, move right by one position during decryption for the first row, two positions to the right for third row, and three positions to the right for the last row. Clear? Any doubts with the first two transformations? If you're having any doubts, do let me know. We have completed two transformations, that is substitute bytes, shift rows. But you haven't asked me yet what about this add round key. Yes or no? Any confusion? Any doubts? How are we going to add it? Any confusion regarding this? Before the actual operation begins, if you remember, there was a phase called as initial transformation. Yes or no? Have I discussed about it? Yes, during the initial discussion. But what about it? What exactly is inside that initial transformation? Can you let me know about that? Yes, come on. Give me your answers. The initial transformation is nothing but whatever plain text we are getting, we are converting that into some sort of a different sort of plain text. So for that, what we do is we simply XOR the initial plain text with the round key. The round key would be nothing but W0 to W3, yes or no. First four words. The second round will be from W4 to W7 and so on. Yes or no? Yes. What about A division? So what we do is after each round, we have this step such as add round key. This addition is not your simple addition. This is simply a modulo addition. If you remember Varnam ciphers, Varnam and Vigner, we used to do the same thing, right? Plain text plus key mod 26. The same thing over here. Similar sort of a thing. Am I clear? Yes or no? Fine now. Can we move ahead? Yes, A division. Raful, Ronak, Tanvi. B division, Simran. Shraddha, Rishikesh, Swardha, Jay. Okay. Okay, fine. So let's move ahead. The third transformation and one of the most complex transformations. If you understand this, then everything else is very simple. A cakewalk. Third and the most important, mixed columns, because we have already seen what is add round key. So I will focus on this last transformation, that is mixed columns. And then AES will be very clear to you. I hope you're understanding this much so far. If you're having any issues, do let me know. If you're facing any issues, do let me know. We still have time. I can focus on this. Okay. Can I move ahead with the last transformation, that is mixed column transformation? Do let me know. Okay. Okay, fine. So let's see. Just let me explain this. Mixed column is basically a substitution operation that makes use of arithmetic over Galois field. Now, what exactly is this Galois field? Any idea what I'm talking about? Whether you have studied this or not? This is a Galois field over 2 raised to 8. You must have heard about fields and groups in your discrete structure subject, if I'm not wrong. Groups, fields, etc. Yes or no? Yes, come on, let me know. It is very simple practically. When I will explain you the concept, you will come to know. You will say this we have already done, but it has got a name, which is a field or a Galois field or Galois field, whatever you want to call it. Any idea? Any one of you knows the answer? Yes or no? Kindly let me know in the chat box without wasting much time. No, fine. So let me explain this. What exactly is this? Whenever I'm saying Galois field over 2 raised to 8, it simply means that whatever operations you perform, that should be bound within 2 raised to 8 only. So the maximum value will be 255 if I'm not wrong. 0 to 255. Yes or no? That is what I said, that whenever you will see the explanation, you will say that we have already done this during our modular arithmetic. Yes or no? Mod 26. No values could be more than 26. Similar kind of concept over here. If I am saying that Galois field over 2 raised to 8, it simply means that whatever values I will get or whatever values I get, that should be within those ranges, that is 0 to 255 only. It can't have any value more than that. Fine. Now is it clear? So the operation over here is mixed column substitution. Mixed column transformation is basically a substitution that makes use of arithmetics over the Galois field 2 raised to 8. I guess 2 raised to 7 is 128. 2 raised to 8 is 256. Fine. It's clear. Can we move ahead? Let me explain. Let me start explaining this. It might get a little tricky, so kindly pay attention. Wherever you want me to explain, wherever you want me to repeat, do let me know. See, basically what happens is mixed column is nothing but your matrix multiplication only. Over here, this is your state matrix. What is a state matrix? We have seen that initially the plain text is converted into a matrix that goes through substitute bytes, that is shift substitute bytes, substitution rows, s bytes. We have seen. After that, we have a phase shift rows. We have seen that also. So once we are out of that shift row phase, whatever matrix we are having, this is that matrix only. Fine. Is it clear? It is nothing but your input. Fine. Any confusion with this? We have already seen two stages before this, that is S bytes or substitute bytes and shift rows. So whatever is the output of shift rows, this is that matrix. Fine. We have to multiply this matrix or state array with a predefined matrix. This you have to remember. It's very simple. Just remember the first row and keep on shifting it right by one bit. You see the first row is 0, 2, 0, 3, 0, 1, 0, 1. Again in hexadecimal values. Second row is 0, 1, 0, 2, 0, 3, 0, 1. So basically it is right shifted by one bit if you see it carefully. Okay, so this is a predefined matrix. You have to multiply your state matrix with this matrix and you will get the answer. Now you will say, sir, how is it difficult? Because matrix multiplication of this sort is very simple. It is 4 by 4. It's not that difficult to do, even manually or even on a calculator. The trickier part over here is you have to do this matrix multiplication over a Galois field of 2 raised to 8. Now just make sure what exactly is a Galois field. Let me show you that. If I'm talking about this value, S dash 0, 0, or I can say it is S dash 0J. If I want this value, I have to use this formula. It is very simple. जैसे आप मैट्रिक्स मल्टीप्लिकेशन करते थे, it is exactly similar. Instead of plus, it will be XOR. It is same. What you need to do is 02 into S0J. That is 02 into this. In matrix multiplication, what we do? We add a plus in between. So instead of that plus, it will be XOR 3 into this. XOR 1 into this. XOR this 1 into 3. Am I clear? Is it clear? So instead of plus, you need to use the concept of XORing. Similarly, what about S-1J? S-1J is nothing but, let me change the color of the pen. S-1J is nothing but this one. And to obtain this, what you need to do is, you need to consider the second row now. So it will be 01 into S0J plus 02 into S1J plus 03 into S2J plus 01 into S3J. And you will get the answer for this. Am I clear? In the same fashion, you have to complete the entire operations. In the exam, you need to write only till this much. But if anyone asks you, how is it performed in real life? You might say it is very simple. Simply multiply whatever value is present over there with the scalar multiples over here. It is 2, 3, 1, and 1. And you will get the answer. Is it that simple? Obviously not. Otherwise, we wouldn't have written over Galois field. We would have simply written it's a matrix multiplication involving two numbers. Yes or no? Obviously, it is not that simple. So what we need to do is we need to perform the multiplication of these hexadecimal numbers over the Galois field. And how is it done? This is only for your understanding purpose. Don't need to write this in your exam, right? I have taken two values as example. What I have done is I've taken two numbers, AF and 08. I want to multiply these values, AF and 8. So basically, we can't write 8. We have to write 08. What we do is we make use of two standard tables, which are called as E table and L table. These are basically lookup tables. Just read it once over here. If we have two hex values multiplied, such as AF into 8, we first look up AF index in the L table. So just check AF in the L table. AF is nothing but A over here and F over here. We will get a value as B7. If it is visible, kindly let me know. AF we have to check in the lookup table, that is the L table, A row and F column, we will get a value as B7. Is it clear? Yes or no? Come on, quickly give me answers. So we are just assuming that we are multiplying two hexadecimal numbers over the Galois field. This is how the multiplication is done. I have taken an example of AF into 8. So first what you did, we first of all converted this AF over Galois field, which came out to be B7. Similarly, now we need to check for 8. 8 is nothing but 0 and 8, and we will get the answer as 4B. Am I clear this much? This much part is clear? Yes or no? It will be B7 and 4B. Now what we need to do is we simply need to add these numbers, B7 and 4B, and it is simple addition. Convert this into your decimal equivalent and add them, and you will get answer as 102. You will get the answer as 102. Fine. Now, how to convert this? What will be the hex of 102? Can any one of you tell me what is hex of 102? Because every value that we are going to get will be in terms of 102, will be in terms of hexadecimal values only. Can we straight away write 102 in hex? Obviously not. We need its representation. Can any one of you let me know what is hex of 102? You can use your calculators, you can use online decryptors, online calculators, whatever you wish. But I want the answer of 102. 66. Okay, let me check. Are you sure? Yes, come on. Will it be 166 or 258? Just check your answers. I got 258. It will be 258. Just check once. Hex of 102 is 258. Just check the tables once again. Just check with any of the online tools available. It is 258. If you remember, what is Galois field maximum value? What is the maximum value of Galois field 2 raised to 8? Can any one of you let me know? 255. Correct. As this value is more than 255, what we shall do? We shall subtract 255 from it, or we shall take mod of it. So we will get the value as 03. Yes or no? Because 258 will not satisfy my Galois field equation. So I have to subtract 255 from it so that the value remains well behind or well within the Galois field conditions. So it becomes 03 in hex. Now it is very simple. You have got the value as 03. Check that in this table, E table, 0 over here, 3 over here. Whatever you will get as answer, that is your multiplication ka result. That is AF into 8 in Galois field 2 raised to 8 will be represented as 0F. It is really very complex. That is why this is not even expected in the exams. But from an understanding point of view, you should know how it is obtained. Am I clear now? You got it, how to do it? So AF into 8 over Galois field 2 raised to 8 multiplication will give you answer as 0F. Is it fine? You will get the answer in your Atul Kahate book. So refer that. I have copy these diagrams from there only. It's a very good book. It is mentioned in your syllabus also, so refer that and you will get the answer. Am I clear with this explanation of mixed column transformation? Obviously, I know today's session was a very heavy session because we have completed the entire topic. Fine. Any doubts with this? And finally, once this is done, you can check your answers with this also. Okay, with this website, hex calculator. 102 minus ff or 255 will give you the answer as 3. So this will be your answer. So now we have completed almost all of these steps. The only step which is left is add round key, that is also I have shown you. Whatever result you get after the mixed column transformation, you have to XOR it with the round key and you will get the output of that round. Similarly, the entire steps will go on till 10th round. The only difference being that in the 10th round, you don't have the mixed column transformation. You simply have substitute bytes, shift rows, followed by add round keys. And after that, whatever output you will get, that will be your ciphertext for that particular round. Am I clear now? Any doubts, any confusions with this, you can let me know. Other than that, I hope this concept is clear. We have completed advanced encryption standard. It is one of the most crucial topics of your syllabus. I will share this PDF with you soon after the lecture. Just go through it and try to understand how it is done. Fine? Okay. Let me drop in the attendance link. If you have any doubts in between, you can kindly ask me, or else we can end this session. Thanks a lot.